So we are joining back with the last section of the welding section of this course. So we have discussed already about several potential welding techniques which are being widely used in industrial parlance in present times, and there are several others which are left that we will be discussing in this class, and then we will go on to discuss about the several welding defects and how to prevent those, and also quality control techniques. So we will start with ultrasonic welding today. So in ultrasonic welding, coalescence is basically produced by the localized application of high frequency. High frequency means between 10,000 to 2 lakh hertz shear vibrations to surfaces that are held together under rather light normal pressure. So in this case, although the ultrasonic vibrations causing heating between the fairing surfaces, the adjoining surfaces. So like for example, you can see the example over here. So you can see, so this is basically a typical lap joint that is formed between the adjacent fairing surfaces. So but however, the heat generated at the fairing surfaces is hardly half of the melting temperature of the individual metal pieces that are experiencing ultrasonic welding. And in this case, likewise, like in case of friction welding and also in case of friction stir welding that we have discussed, in case of ultrasonic welding also, this is a typical solid state welding technique, and we can join similar or dissimilar metals by ultrasonic welding route. So so in this case, because of the shear vibrations, between the fairing surfaces, the oxide layer which is otherwise present, that also gets dispersed, and because of that, oxide layer free and clean metal comes in contact to each other, and coalescence happens between them at the fairing surfaces, and so that high quality weld joint can be produced. So so ultrasonic welding is restricted to lap joint. So that is also a limitation of this advanced welding technique, and it is also limited to thin materials like sheet, foil and wire, or the attaching of thin sheets to heavier structural members. So again, the example of cladding, like we have discussed about in case of roll bonding technique. So that can, similar objectives can be achieved in case of ultrasonic welding also, when we are dealing with the sheet metals and we are trying to append or join another sheet on the top of the sheet metal, that is the workpiece that we are basically subjecting to ultrasonic welding technique. So the maximum thickness is about 2.5 millimeter for aluminium and 1 millimeter for harder metals that the ultrasonic welding technique can handle. So you can all understand from here that there is a serious thickness limitation in this case, which is not there in case of arc welding or resistance welding techniques, and also laser beam it is there, but in case of electron beam welding, that thickness restriction is much lesser. We can but however, every technique has their own merits and own applicability. That is also the case in case of ultrasonic welding. So it is even possible to bond metals to non-metals such as aluminium to ceramics or glass, because the temperatures are low and no arcing or current flow is involved. The process is often preferred for heat sensitive electronic components where heat damage can be fatal, and there ultrasonic welding technique can serve as a recourse, and we can achieve joints without subjecting the electronic circuitry or the electronic components to much of the heat. And the applications include joining the dissimilar metals in bimetallics, making microcircuit electrical contacts, welding refractory or reactive metals, bonding ultra thin metal, and encapsulating explosives or chemicals. So ultrasonic welding has also been used to produce spot and seam welds on thin plastics and to seal foil or plastic envelopes and pouches. So compared to joining methods that employ solvents or adhesives, the ultrasonic welding technique is considerably faster and also much more effective, and results in products with cleaner surfaces. So then we are done with ultrasonic welding, and we will go to another quite interesting welding technique, that is called diffusion welding or diffusion bonding, which occurs when properly prepared surfaces are maintained in contact under sufficient pressure and temperature over a prolonged period of time. So, from the name itself you can understand that diffusion being a slow process, this diffusion welding technique is also a slow technique. However, it can produce very clean joints with significantly improved mechanical and microstructural attributes compared to other fusion welding based techniques. So, in contrast to the deformation welding methods, plastic flow is limited in this case, and the principal bonding mechanism is atomic diffusion. So, this is again a solid state welding technique, like we have discussed in case of friction or ultrasonic or friction stir welding. However, plastification of the metal is much lesser in this case because of prolonged time. So, here the atomic diffusion and atomistic bonding is the primary mechanism because of which two workpieces or two base metals are getting joined to each other. The joint is getting developed. And another important thing is, to promote diffusion we often use interlayer, that is basically to promote between the diffusion atomistic diffusion process between the two base metals. Say we are terming here two base metals as A and B, and then it can significantly improve the diffusion in between them. So, a well prepared interface can be viewed as a planar grain boundary in case of diffusion welding workpieces with intervening voids and impurities. Under low pressure and elevated temperature, atomistic diffusion will provide the necessary void shrinkage and grain boundary migration to form a metallurgical bond. So, the quality of a diffusion weld depends on the surface conditions of the materials, temperature, time at temperature, pressure, and the possible use of intermediate material layers, which can either promote diffusion or prevent the formation of undesirable intermetallic compounds. So, some intermediate layers are designed to melt and form a temporary liquid that significantly accelerates the rate of atom movement. So, this is also a typical example or functionality of the intermediate layers. So, in that case it does not remain a purely solid state welding process, and in that case the diffusion welding also it becomes. So, you can compare this technique with the liquid phase sintering technique that we will be discussing when we will be discussing the powder metallurgy section of this course. So, here so this interlayer when there is faster diffusion faster diffusion rates are needed. So, in that case we promote the diffusion between the workpieces which are subjected to the joint formation by using a interlayer material which also undergoes phase change and causes atomistic diffusion much easier between the workpieces, and so it serves, it accelerates the process of atomic movement. So, the diffusion bonding is frequently used to join dissimilar metals and composite materials. Furnaces with inert or protective environments can be used to produce high quality joints with the reactive metals such as titanium, beryllium and zirconium. And the high temperature refractory metals. So, since the bonding process is quite slow, so multiple parts are generally loaded into a furnace, or the application is restricted to low volume production. So, because of its slow nature, so that is why it becomes only economical when we can get joining between multiple parts. So, that is what is mentioned over here, and of course, it is useful only in case of low volume production, batch production of critical components, where diffusion welding or diffusion bonding serves the purpose. It is not a mass production technique like other welding techniques that we have discussed until now. Explosive welding. So, this is again a typical solid state welding process where the welding process is basically assisted by the explosion of the chemicals. So, in this process a controlled detonation of explosive is used on the welding surface, and this explosion generates a high pressure wave or force which deform the work plates plastically at the interface, and this deformation forms a metallurgical bond between these plates. This metallurgical bond is stronger than the parent material. So, you can understand that the mechanical property of the joint, in this is a particular example like we have discussed at the very beginning, if you may recall, that we can get the joint properties even better than the properties of the individual workpiece material that we are basically joining. So, so this metallurgical bond is stronger than the parent materials, and the detonation process occurs for a very short period of time which cannot damage the parent material. So, this is the basic principle of explosion welding. So, this welding is highly dependent on welding parameters like stand-off distance, velocity of detonation, surface preparation, explosive, etc. So, this welding is capable to join large area due to high energy available in the explosive. So, it is from the name itself you can understand this is a very fast technique in contrast of the diffusion welding technique, which is a very slow process. Here we can achieve joints at a much faster rate with a much lesser time, because the driving force for the joining between the neighboring plates, the faying surfaces, is the is the explosion of the chemical constituent that is kept at the top of the buffer plate. So, you can see, so this is basically plate A, that is termed as base plate. This is the flyer plate, that is plate B, which is getting joined with the base plate A, and this is the distance which is called as stand-off distance between the flyer plate and the base plates. That distance is this flyer plate is basically covering and catastrophically, within a fraction of a second, because of the explosion, that is detonation, controlled detonation of the chemical constituent, and then that pressure pulse is transferred to this flyer plate through this buffer plate. So, the role here of this buffer plate is just to avoid damage in the flyer plate, because objective here to do the joining, achieving the joining at the between the plate A and plate B along their region of interest. So, it is, so we have to avoid the any damage on the surface or subsurface damage in the both the plates, and here because the explosive is kept closer to the flyer plate. So, the chances of damage, surface or subsurface damage to the flyer plate is more, and hence the buffer plate is kept to avoid direct impact of the explosion over the flyer plate. Okay. So, so this welding is capable to join large area at a much lesser time due to high energy available in the explosive. So, the working principles, that number 1 is, first both the flyer plate and the base plate interface surface are cleaned and prepared for good weld. So, so again this, like we have discussed in case of diffusion welding, friction welding, and also in ultrasonic welding, that if generally, if for example, if we talk about light metals such as aluminum or magnesium, there is a high probability of presence of a oxide layer at the top of the workpiece material. So, it is important to clean that oxide layer and properly prepare the surface before going for developing these weld joint. Otherwise, it will cause the weaker joint, and also the presence of this oxide layers within the joint causes the weak link, serves as a weak link which can serve as a region of crack initiation or failure initiation when the weld joint is subjected to the in service loading conditions. So, now the base plate fixed on the anvil and the flyer plate placed at the top of the top surface of it at a predefined distance, that is stand-off distance. So, the flyer plate may be inclined or parallel according to the welding configuration. So, in the last slide we have seen that the flyer plate is kept at an angle theta from the base plate. So, it can also be a case where we can keep the flyer plate at the in parallel to the base plate, and then on the top of that we can keep the buffer plate, and then we can keep the detonator, the explosive. So that is also possible. So it depends on the type of joint architecture that we want to achieve, and also the thickness of the plates that we are trying to join. So based on that we decide on the positioning and the included angle between the base plate and the flyer plate, that whose are experiencing the joining between them. So so the prepared explosive is placed into a box of same size of the welding surface. This box is placed over the buffer plate. So there is a detonator at one side of the explosive which is used to start explosion, and now the detonator ignited the explosive, which creates a high pressure wave. So these waves deforms the interface surface plastically and forms a metallurgical bond between base plate and the flyer plate, and this bond is stronger than parent material. So the types of explosive welding, number one is oblique explosion welding. So in this case, like the previous example, so we keep the flyer plate at an angle theta. That angle varies based on the thickness of the plate and the joint design. So this is called oblique explosion welding. So this welding configuration is used to join thin and small plates. And the other variant is parallel explosion welding, where the faying plate, flyer plate are kept in parallel to the base plate at a certain height, and that height is classified, marked as stand-off distance, and the detonator is kept at the top of the buffer plate with similar geometry to the flyer plate. So this this is useful for welding thick and large plates. So we can understand from here that when the weld joint, when the plates undergoing the joining are thicker in dimension, and also the large heavy objects, so then it is not practical to place them in a angled fashion, because of this included angle kept, although the joining can be faster, the rate of diffusion can be faster. However, it is not easy, or it is not economical to keep such a thick and heavy plate at an angle with the base plate, and which can also cause defect formation and improper welding, improper metallurgical bonding between the plates, the base plate and the flyer plate. So that's why if we go for parallel explosion welding for thicker workpieces, and we take the advantage of oblique welding for thinner plates. Okay. So oblique explosion welding. So the application of explosive welding are, it is used to weld large structure sheets of aluminum to stainless steel. It is a technique where joining can be achieved at a very fast pace, and weld clad sheet with seed steel in a heat exchanger is an example. It is also used to weld cylindrical component like pipe, concentric cylinder, tube, etc. And so the advantages are that it can join similar and dissimilar material. So in this point, it is it is similar to the friction welding and other solid state welding techniques. And it is also the other advantages are large surfaces can be welded at a single pass. So this is one of the major advantage of this explosive welding technique. So the time is involved is much lesser, and high metal joining rate, mostly time is used in preparation of the welding. Actual welding time is much lesser, and it does not affect on properties of the welding material, and it is a solid state process. So does not involve any filler material or the flux, etc. And the disadvantages are, it can only weld ductile metal with high toughness, because brittle material will not get welded, rather it will experience the catastrophic fracture because of the pressure pulse that is very high pressure pulse for a very short period of time, that is passed on by the detonation of the explosive, and it creates a large noise, so that it can only be useful, it can be conducted, performed in a place which is remote from the localization, and I mean it is all of course it is rather very much effective in case of defense applications, and its industrial I mean implementation or industrial applicability is rather limited. So it is a technique which depends largely on process parameters, and it demands for a higher number of safety precautions, and also the joint design is limited. So next is thermite welding. So please recall, we have discussed this technique earlier also. So it is a like a I mean improved version, I mean a typical casting technique. It is like a typical casting technique. So where it is, we are talking about the I mean coalescence is produced by superheated molten metal from the chemical reaction of thermite. So what is a thermite? Thermite is the mixture of pure aluminum and ferrosulfuric oxide, that is Fe3O4, and so they react. So it is basically so they undergo chemical reaction to each other, and then we see that we get Al2O3, that is alumina, and we see I mean pure iron that is getting generated. So I mean so that basically I mean we see the formation of flux and also formation of the liquid melt because of the heat it is generated, because it is an exothermic reaction. So it liberates a significant amount of heat based on this reaction, and that heat is responsible for melting of the I mean this I mean metal. I mean mostly it is used for the ferrous metals for joining. So it is also used for I mean so filler metal obtained from liquid metal, and it is a process used for joining, but has more common with casting. So this is a technique which can be used for places which are remote from a locality where there is not much widespread availability of the electricity as a welding source. So there I mean we can quite effectively use the chemical source as as discussed earlier. So I mean a chemical source. So that's why thermite welding is popular in a remote place, for example railway lines for joining between the tracks. So that can be quite effectively achieved by this I mean thermite welding route. So what is the similarity with casting? So you can see that like we have discussed a typical I mean gravity casting cavity. So we have discussed about the sprue, we have discussed about the sprue base well, then runner, and then ingate, and then also we have talked about the casting cavity, right. So you can see the similarity here. So this part can serve as the I mean sprue base well, and this is like a sprue that is transporting the liquid melt, and then this is like ingate, although the runner portion is much smaller, but it is like a typical casting cavity only that we are I mean doing over here. And so this part also serves like a riser, so which is responsible for feeding of the liquid melt when there is a shrinkage happening at the joint. So this is how we can basically achieve the thermite welding, where also the super hot slag that is formed out of the reaction, it helps in keeping the heat intact. So it does not let the liquefied melt which is prepared within the vessel to I mean solidify, and that is why it keeps the temperature and it keeps in the fluid state, and that can be utilized for allowing it to flow into the joint region, and the joint can be weld joint can be achieved. So the advantages is that it is simple and fast process, and for joining similar or dissimilar metals it is cheap, and it does not need costly power source. The process can be used for places which are remote, there is lacking power supply, and the disadvantages is it is mostly used for ferrous metal parts with heavy sections, and it is uneconomical for welding cheap metals and light parts. So the application, as I told, the railroad rails and repair of cracks in large steel castings and forgings. So it is like a repair technique. So it is can be achieved by local repair of the large castings which are which cannot be scrapped because of the localized failure. So, they can be repaired by thermit welding. So, nowadays there are several repair techniques, even additive, by additive route we also talk about direct energy deposition or direct metal deposition routes. So, they are so they are like recent techniques, and also they deal with a lot of costly energy source like laser, and also the powder or wire form of the metal, whereas in this case it can be very much economical for repair of large castings, where we can use the melt necessary for filling the defected region or the failed region at a much lesser cost with a much more effective manner. So, the weld surface is often smooth enough that no finishing is required, that we achieve by thermit welding route. And then we are moving into the brazing technique. So, brazing is also a technique, welding technique. It is a kind of welding technique, whereas in which a filler metal is melted and distributed by capillary action between the faying surfaces of the metal parts which are undergoing joining. So, base material does not melt in brazing. So, brazing is always a filler metal assisted process. So, in brazing the filler metal has a melting temperature above 450 degree centigrade, but below the melting point of the parent metal that is experiencing joining via brazing route. So, the advantages is that it can be used to join a large variety of dissimilar metals, and pieces of different thicknesses can be joined by brazing. Thin wall tubes, light gauge sheet metal assemblies are not joinable by welding, can be joined by brazing, and complex and multi component assemblies can be economically fabricated with the help of brazing, and inaccessible joint areas which could not be welded by gas metal or gas tungsten arc, spot or seam welding can be formed by brazing. So, it is a versatile technique of welding, and it of course, the joint strength is rather limited, much lesser than the fusion welding or solid state welding techniques that we have discussed so far, but it is quite effective in occasions where inaccessibility by other techniques is a concern, and also cases where it is not the mechanical integrity of the joint is not much of a concern, rather it is the functionally togetherness, and also is of more importance. So, in that case it can serve as a economical alternative to fusion or solid state welding techniques with a rather lesser temperature requirement for the achieving the joint. So, less heating is needed in this case, and disadvantages are, as I told, that lesser joint strength, and it is less than the joint strength is less than the base metal, but is more likely to be higher than the filler metal. So, if you recall, that also we have discussed earlier. We have discussed about the relationship between the strength, joint strength, and also the thickness of the joint. So, then this curve follows this kind of a distribution. So, like a Gaussian kind of a distributions, where there is a optimum thickness of the joint where we can achieve higher strength, and below that so this is like the strength of the filler material sigma f. So, below that thickness, it is because of the capillary force that is not enough. When the joint thickness is much lesser, so then capillary flow of the filler material is not uniform and not achieved properly. So, that is why the strength is lesser, and as and when the joint thickness is increases beyond the optimum thickness, where we get the maximum strength at the joint sigma max. So, then what happens that the strength of the joint decreases, and then finally gets reduced to the finally gets reduced and becomes constant to the strength of the filler material itself. So, this is the case, and then the braided joint can be destroyed under high service temperatures. So, so this is also I mean, this is also a, I mean, concern that it is although a I mean, considered as a permanent joint, however, it experiences failure at high because the melting temperature of the filler material is only 450 degrees centigrade. So, the moment the joint is subjected to temperatures beyond that, it experiences failure. So, this brazing technique is not at all suitable for joining parts which are I mean, exposed to high temperature applications, and brazed joints need high metal cleaning and when done in an industrial setting. So, the joint color is usually different from the base metal, creating an aesthetic disadvantage, and the applications of brazing are: it is used in vacuum interrupters, it is used in transport appliances, used in constructions and helpful in medical equipments. It is also used in art and jewelry. So, these are some typical filler materials for, I mean, brazing. So, filler material based on aluminum and silicon. So, typical composition is aluminum 10 silicon alloy, I mean, master alloy. So, that is a typical composition of the filler material, and also with copper, which is almost pure copper, and their approximate melting temperatures are also mentioned here. It is also copper and phosphorus, copper and zinc alloys, gold and silver alloys. These binary alloys are used as filler materials for brazing, and these are the corresponding melting temperatures, and these are the compatible base metals for this particular filler metals that has been listed over here. And the brazing fluxes. So, the characteristics of a good brazing flux includes low melting temperature, low viscosity, so that it can be displaced by the filler metal and facilitates wetting, and protects the joint until solidification of the filler metal. So, these are the key characteristics of the brazing fluxes. So, I mean, so this is what is listed here, and then on the basis of the method of heating, various brazing processes are torch brazing. So, where flux is applied to the part surfaces and a torch is used to direct a flame against the work in the vicinity of the joint. So, after the work part, joint areas have been heated to a suitable temperature, filler wire is added to the joint, usually in wire or rod form. So, the fuels used in torch brazing includes acetylene, propane and other gases with air or oxygen. So, it is often performed manually and skilled workers must be employed. So, this is the case of torch brazing, which is a manual technique. And furnace brazing, then furnace brazing is a semi automatic technique which is widely used in industrial brazing operations due to its flexibility to mass production and the use of unskilled personnels that it allows for. So, the advantages of furnace brazing is ease with which it can produce a large number of small parts that are easily toothed or self detecting. And then the silver brazing. So, silver brazing is also known as hard soldering. It is brazed utilizing a silver alloy based filler. So, these silver alloys contain many different percentages of silver and other metals such as copper, zinc and cadmium. So, these are the variants of the brazing technique, and there are some other variants also like braze welding, which is the use of a bronze or brass filler rod coated with flux to attach the steel workpiece. So, I mean, so the equipment required for braze welding is basically the same as the equipment used in brazing. And then cast iron welding. So, welding of cast iron is typically a brazing operation which deals with the filler metals, in which mainly the nickel filler rods are made, although true welding with cast iron rods are also possible. The purpose behind this process is to use electricity with copper to hold underground climate pipes warm in cold climates. So, and then there are other brazing techniques are deep brazing, which is particularly suited to aluminum brazing because air is excluded, thus preventing the formation of oxides. So, joining parts are fixtures and brazing complexes applied to mating surfaces, usually in slurry form, and then the operation is done. So, after placing the filler metal at the adjoining surfaces, they are basically undergoes melting at the application of the heat by the brazing torch. And then then the vacuum brazing is a material joining method that gives vital benefits such as extremely clean, superior flux free brake joints of high integrity and strength. So, this process is expensive because it must be done inside a vacuum chamber vessel. The temperature uniformity is maintained at room temperature when heated into in a vacuum, reducing residual stress formation due to slow heating and cooling cycle. So these are the nuances of the brazing processes, and here comes the soldering. Soldering is very similar in operation with brazing and can be defined as a joining process in which a filler metal with melting point not exceeding 450 degree centigrade like brazing is melted and distributed by capillary action between the faying surfaces of the metal parts being joined. The typical example of soldering can be the electronic circuits that we and its components that we generally observe in case of television sets, and also motherboards, etc. So, as the difference is that in case of soldering, the temperature range is even lesser than brazing, and it is a kind of joint which often termed as semi permanent in nature because of its very low temperature applicability. So, the moment temperature goes beyond 300 degree centigrade, soldering joint totally fails. So, the lead, silver, tin antimony or tin zinc based filler metals are generally used in case of soldering, which are listed over here, and their approximate melting temperature is also listed in this table. So, but in general, alloys of tin and lead are generally used as solder material. Tin is chemically active at soldering temperature and promotes the wetting action required for successful joining. So, so the primary difference between the soldering and brazing technique is soldering works at a lesser temperature. It deals with a lesser temperature, lesser melting temperature filler material, and number 2 is that soldering deals with the narrow joints where the post melting the filler material flows and occupies creates the joint by capillary flow. So the capillary action between the faying surface is responsible for joint formation. So, and similar like brazing, here also no melting of the base metal happens. So, the filler metal is called solder is added to the joint, which distributes itself closely within the joint post melting. So, the advantages are it is a simple and economical process since it has done at relatively low temperature. So, no metallurgical damage happens to the base metal. The soft solder joint can easily be dismantled by simple heating, and the operator fatigue is less compared to the welding process. And so, soldering can be divided into two classifications, that is soft and hard soldering. And disadvantages are the process is limited to the minimum thickness, beyond 3 mm it is often fails to create a appropriate solder joint, and it demands for a certain skill set of the operator, and the strength of the joint when compared to weld joints, either fusion weld or solid state weld, it is much weaker compared to those joints, and that is why it is mostly being applied for electronic applications and not for structural load bearing applications. And its applicability is used to join like automotive radiator cores for plumbing, used in electronic industries like radio, TV, computers, and it is also used for joining wires and cables to lugs in electrical industries. So, so that so there are so with this we are done with the this brazing and soldering technique. So, we will discuss about the resistance welding processes, and also about welding defects and quality control techniques in the next class. So, we are stopping here for this class. Thank you.